Hello everyone and welcome to today's lecture. So today what we plan on doing is going over Fourier series and kind of introducing some of the main ideas of Fourier series. This is a good example to think about while we're kind of going through this is the last example of the previous lecture, which was actually the first four terms in the sine series for the function that I gave in the example. So in general, the Fourier series represents an analytic instrument that enables us to work with periodic functions. So I'll write this down. And this is an extremely important tool when it comes to signals processing and signals analysis. But that's not all. It has many other very important mathematical and applied applications. Specifically, one of the applications that we'll see in a little while is that we can use the Fourier series to solve very special types of boundary value problems for partial differential equations. As well as we can use it to investigate solutions to ordinary differential equations. So it's a very versatile tool in many respects. So we'll begin by a simple example of such a periodic function. This is a function of the form y of t is equal to a times sine of omega t plus alpha, where t denotes possibly time, but you could also do a Fourier expansion in any other variable x, y, or z. I just like using t for the independent variable. Omega here, in this example, is the frequency of this curve, the cyclic frequency. So if you graph out what this looks like, right, this is going to be the exact frequency of some sine wave. This is measured in radians per second. Of course, if t denotes time. If t denotes some other variable like distance, say, it'd be measured in radians per meter, or whatever length unit of length you're using for the variable. It's the independent variable. A here is the amplitude. And alpha is called the initial phase of this sine function. Because when t equals 0, you get the equation a times sine of alpha. So that's going to be the value of this function at t equals 0. So alpha is directly related to this value of t, the initial value of t. Now, it's important to note here that if we have a function of this form, that the period of such a function will be 2 pi over omega, whatever the cyclic frequency is. Right? Because when we plug in t equals 0 here, we get a times sine of alpha, which gives us the initial value, or the value at t equals 0. And then this will start repeating itself when we hit the value of t, lowercase t, equal to capital T, 2 pi over omega. Because when you plug in 2 pi right here, you get over omega, you get just 2 pi. And sine of alpha plus 2 pi is the same thing as sine of alpha, because it's the sine function is 2 pi periodic. This is very cool. So, for example, if omega is equal to 440 times 2 pi radians per second, there are 440 cycles per second, and this is the frequency of a standard A of a violin string. So this is very cool. And this gives us, kind of brings us to this idea of what are called overtones, which are simple motions or tones of multiple frequencies. Right? And the sum of a finite number of such overtones is a sum of the form y of t is equal to a1 times sine of omega t plus alpha 1 plus a2 times sine of omega t plus alpha 2 plus all the way up to a1 times sine of omega t plus alpha n. And this is a periodic function. Of this argument omega right here. Specifically, it's a periodic function of, not omega, but the period 2 pi over omega, because every term in this sum possesses a frequency of omega. So, for example, if you go through and check the periodicity of this function, and this function, all of the functions in this sum, they're all going to be 2 pi, have a period of 2 pi over omega. So the function as a whole will also have a period of 2 pi over omega. So let's consider the following. We'll consider a generalization of this idea of overtones. We'll consider this idea of expressing the following. So let's take a function f of x that has a period of capital L. So that f of x is equal to f of x plus L is equal to f of x plus 2L, and so on and so forth. For any integer, this is all the way equal to, for any integer L, for n, f of x plus n times L. For any arbitrary integer n. So the main hypothesis here that we're going to see is true is the following. So this is based directly on the last example of the last lecture. We expect that for every L periodic function f of x that satisfies some mild conditions, which I'll get into a little bit more in a little bit more detail later on in the lecture. Let's say satisfying some mild conditions here. We can expand the function into an infinite series, right? In an infinite series of the following form. F of x is equal to coefficient a naught over 2 plus a1 times cosine of x plus b1, and this should be not just x here, but we want to respect the general period L. So cosine of two pi x over L plus b1 sine of 2 pi x over L plus a2 cosine of 3 times 2 pi over L x plus b2, not 3, sorry, but 2 times 2 pi over Lx plus b2 sine of 2 times 2 pi over Lx, so on and so forth. All the way up to a n cosine of n times 2 pi over L x plus bn times sine of n times 2 pi over L x, all the way to infinity. So there's a lot of mathematics that goes on with dealing with the convergence of infinite series, and you have to be very, very careful when you're talking about the types of convergence for an infinite series. And we will get into this a little bit more in depth in the lecture, but the idea here is that this is all based off of this idea right here, the idea of overtones, because this is the same thing as, you can think of it as just the sum of sines and cosines, and this is a finite series with the same frequency. Well, essentially what we're doing is we're saying that a given periodic function, say, for example, the function from the last example of the last lecture, which was f of x is equal to x times pi minus x. This was a function that went from 0 to pi, and it looked like this. And so we expect that based on the approximation from the last lecture, that if you do that approximation for infinitely many a1s and b1s, in this case just sines, and we'll see why it's just signs a little bit later on in the lecture. For this example, you'll get a function that converges to something like this, which is just the function itself repeated over periods of length pi. And this is exactly what happens. So a nicer way of writing this infinite series, the Fourier series, is a0 over 2 plus the summation from n equals 1 to infinity of an times cosine of n pi over L times x plus bn times sine of n pi over L x. Right, this is going to be 2n pi over L. This is going to be 2n pi over L. So in general, if you look at a function of this for the sum like this for a finite sum, you're going to see that it's some periodic function. It'll have period L, because each one of these functions has period L. But the idea is, these have they have periods of frequencies of higher and higher and higher value as n increases. So they're getting finer and finer and finer. And the idea is that the decomposition that we get when we do Fourier series is directly related to the idea in the very last example of the last lecture. So the an and the bn here is just a sequence of constants that depend on n. In, say, for the third term, you get a3 times cosine of 6 pi over Lx, right, which is an oscillatory function. And we can go through here and see that each one of these terms is going to represent a periodic function at a given frequency, 2 pi times n over L. Now, it's important that we make a following kind of assumption that I'm going to kind of gloss over the idea of term-wise integration. We're going to assume for now that we can integrate term-wise, which is in fact a very big assumption. There are some big mathematical things that you need to do to justify term-wise integration. But for the purposes of kind of showing what we're doing with Fourier series, I'm going to gloss over this and assume the following things about our function. So the first big assumption is that for now, and we'll see how to justify this a little bit later on, that the trigonometric series converges to the function f of x. 2 is that it can be integrated term-wise. But the idea here is the following, that if these two assumptions are true, which there are ways of going through and justifying when this is going to actually happen, but these end up being valid assumptions under certain scenarios. So we will get into a little bit later what the conditions on f are that make this a valid computation. But the idea is that what I'm about to do is a very extremely valid computation, as long as f satisfies the a and the bn satisfy certain conditions. So we consider the series, and specifically we consider what happens when we multiply the series by cosine of mx and then integrate. We integrate from negative L to positive L of f of x times cosine of mx dx. Remember that from the previous lecture, this can be seen as the same thing as taking the inner product, the function inner product of the function f with cosine of mx. With the weight function of p of x equal to 1. So this is the same thing as, if this expansion is true, the inner product of this infinite sum, a naught over 2 plus the summation from n equals 1 to infinity of cosine of 2n pi over L x times an plus should probably include this on a lower line so we can fit it in a little bit better. Bn times sine of 2n pi over L times x with cosine of mx. And in terms of the integral, this is the same thing as looking at, well, a naught is a constant, so this usually becomes the integral of a naught over 2 times the integral from negative L to L of, oh, and this is cosine, sorry, not cosine of mx, but cosine of m 2m pi over L. If L is 1, things will simplify, or sorry, if L is 2 pi, things simplify a lot, because you just get cosine of mx. But I like doing this in general for a general period because of the fact that this is how we're going to be using it in applications. And this should be 2m pi over Lx. That's the sum of this plus then the sum from n equals 1 to infinity of an times the integral from negative L to L of cosine n, or 2n pi over L times cosine of 2m pi over L dx. And then plus dn times the integral from negative L to L of sine of 2n pi over L x cosine of 2m pi over L times x. We'll just move this over a little bit more so we have room for dx here. In slightly shorter notation, right, we have that the inner product, the function space inner product of f with cosine of 2m pi over L x is equal to a naught over 2 times the function space inner product of 1 with cosine of 2m pi over Lx plus the infinite sum from n equals 1 to infinity of an function space inner product of cosine of 2n pi over Lx with cosine of 2m pi over L times x. And let's bring this onto the next page so we have a little more room to deal with. Lastly, plus dn times the function space inner product of cosine of 2n pi over Lx, or cosine of 2n pi over Lx. Cosine of 2m pi over Lx. We can look at each one of these inner products and see what's going to happen. And we have something that's remarkable here. The integral from negative L to L of cosine of nx cosine of mx, 2n pi over Lx cosine of 2m pi over Lx. If we go through and calculate this, sorry, so I just realized I had a little bit of a typo here. The integrals should be over one period. So if the period is L, that should be from negative L over 2 to positive L over 2. And that's true for all of the previous integrals or function inner products that we've calculated. But when we go through and do this integral, I recommend that you check this. we end up getting that it's 0 when n is not equal to m. It's L when n is equal to m. And it's 2 pi when n is equal to m is equal to 0. It has to be greater than 0. So you can go through and do this integral using the technique that I showed before from Calculus 2. It would be really good practice for you to go through and check this. Likewise, we can go through and calculate the sine and cosine, or sine times cosine inner product, which ends up being the integral from L over 2 of sine of 2 pi n over Lx times cosine of 2 pi m over Lx. And this will be equal to 0. Essentially, the easiest way of showing this is because sine on this symmetric interval is an odd function. Cosine is an even function. Therefore, sine times cosine is an odd function. And therefore, the integral will be 0. However, you can also go through and calculate directly using the tabular integration by parts method. So, I recommend going through and checking this just like before. It's very similar to the example done in the last exercise, the last lecture. But what's amazing now is if we look at this summation, we get a simplification. Actually, two main simplifications here. And we'll look at each one of these in turn. Remember, the whole goal here is to solve for the coefficients a naught, and then the infinite set of coefficients a n and b n. Well, when m is equal to 0, this inner product right here ends up being equal to just L. And because of our orthogonality relations, each one of these is also going to be 0. So if you look at each one of the integrals here, when m is equal to 0, if the inner product of sine with 1, the inner product of cosine with 1, and the only integral that will be non-zero will be this integral right here, which goes to L. Based on the calculation that we did before. So this equation reduces to the equation that the inner product of f with 1 is m is 0, so cosine of 0 is 0, is equal to a naught times L over 2, or a naught is equal to the integral of f of x dx times 2 over L. Which is the definition of the first Fourier coefficient. Now, move this onto the next page so we have some more space. In general now, when m is any positive n, so m is any positive natural number greater than 0, from the orthogonality relation, we know that this is going to be equal to 0. And from the other orthogonality relation that we calculated up here, you know that this is going to be 0 unless m is equal to n. In which case, it goes to L over 2. And this integral right here, instead of 5 right here, will be equal to 0. So we're left with a single equation that the inner product of f with cosine of 2 pi m over Lx is equal to am times L over 2, which gives us the equation that am is equal to 2 over L times the integral from negative L over 2 to L over 2 of f of x times cosine of 2 pi m over L times x, which gives us an exact equation for all of our AMs. And what's amazing is that we can go through similarly and do this exact same process, starting at the very beginning by multiplying the series by not cosine of 2 pi m over Lx, but sine of 2 pi m over Lx. And sure enough, when we do this, we get the equation that two over L, so Pm is going to be 2 over L times the integral from negative L over 2 to L over 2 times f of x sine of 2 pi m over Lx. And this is really quite amazing because this is essentially giving us, right, that we have an exact way of going through and expressing a given periodic function in terms of an infinite series of sines and cosines. And we know exactly what the correct values for the coefficients in those sines and cosines are just by taking integrals. This is giving us what this is an idea of taking our function space I haven't specified what that function space should be, but we're looking at the basis of functions. 1 sine of 2 pi over Lx, cosine of 2 pi over Lx, sine of 4 pi over Lx, cosine of 4 pi over Lx, all the way to infinity. So this set of functions, or vectors, if you will, in the function space. And we're calculating the, first off, by calculating these integrals right here, you're showing that these functions are orthogonal in the function space. And not only that, these functions, right, are being used to find the best expansion for a function f. And we're going to see that the best expansion is actually an exact expansion for the function f. Now we can go through and generalize some of the assumptions and some of the things that f needs to satisfy. But let's go through and see an example of how to use this, just so that we're all clear. So we'll consider the following example. We'll do a type of sawtooth wave. With period 4, which is one of the many common signals. That you would see in a signals processing application. And so start by the sawtooth function. The sawtooth function is defined as, there's a number of different ways of writing it down, but x minus the 4 function of x. Where the 4 function is just the function that no matter what the decimal value of x, rounds it down to the nearest integer below x. And this function looks like the following. Looks like the function x on the interval from 0 to 1. So y equals x. But it's periodic in that for every positive interval, it's going to look like this, as well as every negative interval. So we'll consider the sawtooth function. Say f of x is equal to negative x minus 4 times the floor function of x over 4 plus 3. I'll take a look at this in Desmos. So I plotted out the sawtooth function, and now I'll also plot out this function right here. So we're looking for the Fourier series expansion of this function right here, the blue function, which is a scaled, shifted version of the floor function itself, and this new function has period 4. So you can see that just by maybe plotting this out, you see that it's going to be negative x plus 3. So on this interval, these two things are identical. So this will be essential when we go through and calculate the coefficients. So let's go through and do that. The first coefficient is going to be a naught, which is the integral of 2 over L times the integral from negative L over 2 to L over 2 of the function f of x dx. And this is where we can very, very effectively apply what I just showed, which is that this function is the same thing as the function negative x plus 3 on the interval from 0 to 4. And because of the periodicity of this function, so if you think about what this function looks like, so using that plot that we just created, I will open up and copy it over so we can kind of see it. So this sawtooth function that we're investigating, which is our f of x here, so f of x is the blue function, because of the fact that this integral is from negative L over 2 to positive L over 2, the integral of the blue function from here to here is going to be the same as the integral of the green function from 0 to 4. Or negative x plus 3 integral from 0 to 4, which is really cool. And so this is going to be 2 over 4 times the integral from 0 to 4 of negative x plus 3 dx, which is 1/2 times negative x squared over 2 plus 3x from 4 to 0, which will be 1/2 negative 16 over 2 plus 12, which will be 12 minus 8 over 2, or 4 over 2, which is just equal to 2. So A naught is equal to 2. For AN, this is going to be the integral from, or 2 over L times the integral from negative L over 2 to L over 2 of f of x times sine or cosine of n pi x times 2 over L and going through and calculating this integral might be tricky, just like before, because if you split it up into parts, unless you use the fact that, again, right, these are both periodic functions of period L, so this will just be 2 over 4, which is 1/2 times the integral from from 0 to 4 of the function negative x plus 3 times cosine of 2n pi over L, or over 4, which is n pi over 2 times x dx. And when we go through and evaluate this using integration by parts, this becomes an is equal to 1/2 or fully simplified ends up being negative pi times m times sine of n, or pi times n times sine of 2n pi minus 2 cosine of 2n pi plus 2 all over m squared plus pi times pi squared, and sine of 2n pi will always be 0. Cosine of 2n pi will always be 1. And so an here is going to be equal to 0 for all values of n, because you get 2 minus 2, which is 0. Now it's important to note here that many times you get expressions when you go through and calculate these coefficients that may be of the form of cosine of not 2n pi, but n times pi. Okay, we know that from the graph of the cosine function, cosine of n times pi is actually going to be negative 1 to the n. It's going to be negative 1 when n is even, or when n is odd, and it's going to be positive 1 when n is even. So just be careful of this for your Fourier series expansions in the future. But the idea is that the last coefficient bn, the last sequence of coefficients, will be 2 over L times the integral from negative L over 2 to L over 2 of f of x times sine of n pi over 2x, or put the general formula here, 2n pi over L x dx, which just like the same reason as the other integrals, because of the periodicity of the functions involved, is the same thing as the integral of this function over the interval from 0 to 4, which is the function negative x plus 3 times sine of n pi over 2x dx. This is going to be then 1/2 times this integral, which ends up reducing to, after you do integration by parts on this, 3 pi times m minus 2 sine of 2n pi plus m pi cosine of 2m pi. And that's divided by pi squared times n squared. And again, sine of 2n pi will always be 0 for any value of n. And this should be n right here. Cosine of 2n pi will always be equal to 1 for any value of n. So the Fourier coefficient bn simplifies to 4 pi m, because you have 3 pi m, 3 pi n plus n pi, which is 4 n pi divided by pi squared n squared, and you end up getting 4 divided by pi times n. So that means that we should have that our function, f of x, this special sawtooth function that we're looking at, should be equal to the Fourier series. And the formula for the Fourier series, remember, is a naught over 2 plus the summation from n equals 1 to infinity of an cosine of 2n pi over L x plus bn times sine of 2n pi over L x, which simplifies when you plug in a naught, you get 1. All of your a-n's are 0, and all of your b-n's are 4 over pi n. 4 over pi times n times sine of n pi over 2 times x. And we can open up our Desmos window to take a look at this. And so let's do this right now. So period of 4, our a naught value that we calculated is 2, an is 0, bn is 4 over pi n. In the Fourier series is this summation right here. And we'll play the animation that just increases with values of n. So we're going to go for n, or the maximum term in the summation, from 1 to 100. And we see very clearly that as n gets larger and larger and larger, we're getting closer and closer and closer to the sine function, the sawtooth function, the sawtooth wave that we started with. This is really incredible. You can kind of take a look here at the actual value of the sawtooth function itself if I color it in red. So you can see it right here, the sawtooth function in that old function, right, negative x plus 3, matches the sawtooth function in this interval. Right, it's exactly matching, and the Fourier series is converging to this. If you zoom in very, very far, there is error. Right? But as n gets larger and larger and larger, this error is getting smaller and smaller and smaller. So this is really incredible, and this is the idea, the heart of Fourier series and using Fourier series in signals analysis. One of the things that we're going to see is that the Fourier series even converges on these discontinuities, and any really discontinuity point of the function inside this interval. So one of the things that we'll see is that for the Fourier series is going to be valid. It's a valid procedure for piecewise continuous functions when the Fourier series is what's called uniformly convergent. So we'll get into what that means in a little bit, but I'll show you a picture of what this means. Right, this means that even the Fourier series will even converge at these boundary points right here, and it'll converge exactly to the limit of the function, the average value of the limit of the function from the right, plus in the limiting value of the function from the left. So in this case, it's this point right here. In this case, it's this point right here, and so on and so forth. So this happens at every point. But we'll make that more specific in a little bit.